So we're going to change gears now and actually go very close to the volcano and use geophysics to look under the ground and see what that can tell us about proximal to medial deposits. This is really important from a hazards perspective because the information that we can get from these deposits can inform the models that we use for hazard mitigation, Tephra sedimentation models, which are really important both before a crisis and after and during. And there's lots and lots of these models, but the majority all use different version. Well, they all use the advection diffusion equation. They use different methods to solve it, and they make different simplifying assumptions. This is one example of this mass conservation equation. It's not the full parameterization because it's not fully 3D. But you can see the main features that are involved in these models. There is a in here? A source term, and then particles are, oh, I like pointing. Particles are Particles are advected by the wind, and they diffuse through the atmosphere and sediment onto the ground. So there's different ways of solving this, but those are generally how these models work. So just from looking at those equations, if we consider a more simplified scenario, and by simplified scenario I mean a simplified Winfield, we know what deposits would look like if this equation is a good way of modeling Tephra fallout. Just based on the equations, we know that the thinning trend of the deposit would be Gaussian in the crosswind direction. It will thin exponentially with distance from the vent. So if we had a situation where the wind was constant in one direction, deposits should look like this if this model is a good approximation of the reality. Some of the parameters in the model that make the most difference when we run them are the column height, the wind field is big deal, and the amount of mass that's injected into the atmosphere. And especially closer to the vent, the diffusion coefficient plays a role as well. And these are sort of the main parameters if you do a sensitivity study that are going to affect the output. I'm going to talk more about the diffusion coefficient later. So how these models tend to be validated is you go out after an eruption and you maybe do sampling of pits in the medial zone, and you run your model and you compare it to the pit data. This is an example of one of the models, the Tephra 2 model, comparing it to the deposit at Cerro Negro after the 1992 eruption, which I'll give you some details on in a minute. If the model was a perfect fit to reality, all of our data points would fall on this line such that the observed accumulation equals the calculated accumulation at every place that we sampled. You can see here that this is the medial zone, and it does a pretty good job. This model does a pretty good job in the medial zone for this eruption. If you look over here, we have very few data points, but we have a few data points. This is the proximal zone. It's thicker here. And you can see that the model is under-predicting the thickness in that zone. And this is very common with these models. Pretty much all of them will under-predict sedimentation in the proximal zone. There's a few reasons for this. One is simply that we don't have a lot of data in proximal zones. You can't hand dig trenches in proximal zones, so we don't really have a lot of data to compare and to inform our models to begin with. And another reason is that there's different sedimentation regimes. And in the medial zone in general, fallout is occurring from the buoyant plume. In the proximal zone, you have more complicated physics occurring because you have fallout from the eruption column margins is impacting in that region. Now I mentioned that in the proximal region it's more difficult to sample because you can't just dig a pit. As a solution to that, you can use geophysics. So this is a ground penetrating radar. This is one of the unshielded ones that are awesome that you can't buy anymore. And this is 50 megahertz antennas. These are the antennas. There is a transmitter and receiver antenna. This is sending electromagnetic waves into the ground where they reflect off of changes in the electrical permittivity, come back up to the receiver antenna. Up there is our GPS. And in the background is the backpack with the computer where we control things. Now, the person with the backpack has to walk behind because we don't want the electrical signals from the computer to interact with the radar signals that we're sending into the ground. So just sort of how that works schematically, you send an electromagnetic pulse into the ground. Whenever there's a change in the electrical permittivity of the material, that can lead to a reflection, and then you retrieve that signal. So by dragging this along the ground, you can build up an image of the subsurface. You can see things like buried bombs and blocks, as well as different units, as long as those units have some change that the radar waves can detect. So it's actually really good at detecting changes, sudden changes in particle size, because that's a change in porosity. And so that affects the electrical properties of the deposit. Also, if you've had time to build up a soil, that has very different electrical properties, and that will also cause a very strong reflection in the radar. So these on the Tephra blanket are the two general things that are going to be causing reflections. And this is great because it allows us to recognize significant changes in eruptions, during eruptions, and also differentiate between different eruptions. So this is me at Cerro Negro volcano in Nicaragua, where I have done studies with this radar on the Tephra. So Cerro Negro is located in northwestern Nicaragua. It's a scoria cone. So it first erupted in 1850. It's erupted 24 times since. And eruptions tend to be characterized by plumes reaching 4 to 7 kilometers into the atmosphere. The most recent larger eruption was actually in 1992. That eruption is well documented. It had, well, most of the eruptions are documented to some degree. And the 1992 eruption had a column, was 7 kilometers high for the first 6 or 7 hours. And after that, sort of transitioned into a weak plume, bent over by the wind, for another 14, I'm a little off on my numbers here, but about 14 hours. So in 2007 and again in 2011, we went in with in 2010, we went in with the radar and we collected profiles on the Tephra blanket. This profile D follows the downwind direction that you can really see when you're at the volcano. And then we have these 3 crosswind profiles. This is what the data looks like. It's very interesting, actually. So we did drag the radar by 3 different sample pits where we had determined the base of the 1992 eruption. So here, profile E, which is blue, that marks the base of the 1992 eruption. We know that. Then if you look at the radar closely, you can see that the characterization of the returns is different below the red line. And that's the pre-existing surface. So we know the pre-existing surface and the first eruption, and we know the base of the 1992 eruption because of those pits. We don't know differences between other eruptions. So I don't know when the 1995 eruption, well, that's actually really small on top of the 92, but I can't label the transitions to any of the other eruptions. But I wanted to be able to say something about deposits generally in this location. So I picked the brightest horizons that you can follow for hundreds of meters. So these represent significant changes. I don't know if those are changes within eruptions or if they are changes between eruptions. And guaranteed, some of the packages, a package is just any unit between any 2 colors, that's a package. And definitely some of these packages will contain tephra from multiple eruptions, and maybe some don't, and that's fine. Because we're looking at generally how to characterize deposits at this volcano. And if you remember what I said about what's predicted by the advection diffusion equation, something I forgot to tell you about Cerro Negro is that it actually does have very constant, fairly steady trade winds in the area. So the majority of these eruptions have been erupted into very similar wind fields that are fairly simplistic. So then we look at the thinning trend of profile D. And if it's an exponential, just like we expected from the advection diffusion equation. But you'll notice that deposits become over-thickened at this distance of about 12 to 1400 meters from the vent. We identify this as the column corner. So this is identified as proximal deposit, and this is medial, which means that this is being impacted by fallout from plume margins, and this is from the buoyant eruption plume. And yeah. Now, more work has been done on these regime changes for larger eruptions. But if we borrow the equations that have been, the empirical relationships that have been derived for larger eruptions, you can determine things based on the location of that corner. You can determine the maximum height of the eruption responsible. So for the majority of eruptions that are depositing material at Cerro Negro, they tend to be characterized by column heights of 6 to 7 kilometers according to these relationships. And we know from the historical records that this is true. The eruptions that put out the majority of material are characterized by column heights, maximum column heights of 6 to 7 kilometers. This is one of the Crossbone profiles. This one is closest to the vent. It's only 700 meters from the vent. Again, we've picked the brightest horizons. They're not necessarily correlated to eruptions. And these ones we expect to be Gaussian if we can apply the advection diffusion equation. Here's the central crosswind profile and the farthest. These are remarkably Gaussian. I don't have the correlations, but these are amazingly Gaussian, which is great. And it means we can do some further analysis as well. Which brings me back to the diffusion coefficient. This is an interesting parameter in these models because in general that we don't really have a way of measuring it. And so some people will even call it a fudge factor because if the model's a little bit off, maybe you can change your diffusion coefficient and get it to fit a little bit better. And the truth about that is that really you have to calibrate the models, and then luckily the diffusion coefficient, as long as you're within about an order of magnitude, you're going to be okay. It's not crazy sensitive to this parameter. It's more sensitive the closer to the vent you are with linear diffusion, but as you get farther away, as long as if you change the model within an order of magnitude, it doesn't affect the output of the model that much. We can calculate it from these deposits based on the width of the Gaussian. And as far as I know, this is the only time that this parameter has been calculated from a deposit and compared to the models. So this range, it's 266 to 762 meters squared per second for the diffusion coefficient. That's hardly anything. That's not a big range, which is great. It means that not only are the diffusion coefficients staying within an order of magnitude in real life, so that if you're sort of in the ballpark, you're probably going to be okay, but also these are the values that we use when we model this volcano. So this has sort of validated our use of this parameter. But we can do even more. So if you take the standard deviation of those Gaussians, this is another one of those empirical relationships derived for larger eruptions, you can calculate the fall height, the location where those particles are sedimenting out of the plume. And for the proximal zone, we have calculated fall heights of 1 to 2 kilometers. So this means that as material rises in the eruption column, material is shedding off of the margins and sedimenting in this area, and it's only falling from this distinct location of about 1 to 2 kilometers. And farther out, material is falling, sedimenting from the buoyant plume, which is more like 4 to 7 kilometers in height. So what have we done? we've used the GPR to characterize the shape of the deposits, the thinning trends. And we have found that for the simplistic case of a fairly constant wind field, these models do a fantastic job of reproducing the actual deposits because the basic mathematical predictions are validated. And we've also found that the region responsible for sedimentation in the proximal zone and in the medial zone are distinct. The interesting thing about that is the models, as I said, do a poor job in the proximal zone. So this implies that if we want to do a good job in this zone, we need to characterize the material as sedimenting from those locations, and it's a separate process from what's happening farther out. But it is still governed by the linear diffusion, and the diffusion coefficients are of similar magnitude to those farther out. And so the main difference is where the material is coming from, as well as the particle sizes. And this is just a shout out to the collaborators. Chuck Connor and Sarah Cruz are actually the co-authors, but Laura Connor, she's sort of the master behind the Tephra 2 code, and she helped out a lot. And this is Geophysics Field Camp that helped collect a lot of data. So, thanks.
The questions for Leah? Yeah, what's the maximum depth of the GPR? Like, could you take it onto the main cone and go deeper?
So on the Tephra blanket, we're seeing down to about 20 meters. So depth is dependent on the frequency that you use. And we can see down to over 20 meters. On the cone, you don't get as good penetration. I actually have a completely separate study where I characterize the cone. And you see about 10 meters. But it's really great because you get these nearly continuous profiles. It only takes about an afternoon to collect the data. And it's just beautiful. Tephra provides beautiful reflectors for ground penetrating radar.
So maybe I'm not interpreting these profiles correctly, but you were running your profiles across a trough, and then you're converting those to a thickness, like basically removing the underlying topography of that trough?
I should have said, so this is the topo-corrected image. So we are, and it's not actually, so it's a vertical exaggeration. So this is a lot more topography than there actually is, but this is just so that you can see the topography. So you're basically running over an approximately flat surface. Does that make sense?
But
So within the deposit, as you're curving around, this is the axis of maximum deposition. So that's why it gets steeper. There's more material deposited here and less deposited out on the sides.
So that's not sort of an underlying structure?
No. That's just the thickness of the tephra. It's not sort of a structural, it's tephra thickness. Just like if you imagine a pre-existing flat topography and then you had an eruption, it would sort of build up the Gaussian. If you sort of invert that so that the surface is actually more flat, it's going to be thicker in the middle.
Maybe one thing that's confusing is the upper surface is the ground surface, but it's not adjusted for the actual topography on the surface.
This one is.
Okay, the upper one is not though.
No, the upper ones are not. So once it's adjusted, it doesn't look like a bowl anymore, but it's thicker here and thinner out on it.
Do you see lava flows interbedded with your tephra?
No. There are lava flows at Serra Negra. They would all be over here. And it's not a particularly good reflector either. We've looked for at least near surface dikes and had some issues.
So what would it look like if there was just one lava flow?
It would probably just look like a bunch of noise and discordant. It wouldn't provide a clear horizon.
Other questions?
What is the frequency of your signal? Is it variable?
Of the radar signal?
Yeah.
The center frequency for this study is 50 megahertz for the to get deep, and then we run over the same profile with 200 megahertz for better resolution, but that doesn't see as deeply.
But then you have to change the antennas.
Yes, you have to change the antenna.
Could those little bright spots in between each of those layers, could they just be like different pulses, and so you get different like agglutination layers or something like that?
Well, yeah, and there's nothing special about this horizon versus this horizon that I didn't pick, or this one that I didn't pick. I just went for whichever was the brightest and easiest to identify. But yeah, I don't know what they actually stand for. They could be eruption pulses. They could be a little bit of ground cover. Without trenching, I have no way of knowing.
I mean, this is, did you do a typical reflection survey to compare to this? With still
Seismic?
Yes.
No.
Okay.
No.
To compare with geophones?
No, but we did run CMPs with GPR. So seismic would look much deeper, and seismic wouldn't have reflections off of the different Tephra deposits. There's not enough density variation. So it creates an electric signal, but it wouldn't create a seismic signal.
Do you think you get multiple refractions since you have such good reflectors in your series? Do you think you get multiples from them?
We definitely do get multiples, and but you can tease those out because mathematically you know where to expect them. So yeah, there are multiples, but we've accounted for that.